Hello friends, welcome to this tutorial. Here we will discuss on LeetCode problem number 3508, which is implement router. Let's go to the description. So we need to design data structure that can efficiently manage data packets in a network router. So we have given this router. Each packet can contain source, destination, timestamp, right? And then we need to implement this router class. So we have this first constructor. So this has a input parameter as memory limit. So here the memory limit is the maximum number of packets a router can store, right? Now if there is any scenario where the number of packets exceed this memory limit, then we need to remove the oldest packet from the router. Okay. Next we have this add packet. So this add packet has a input parameter as source, destination, timestamp. Okay, we need to insert the combination of this packet in the router. But first we need to check whether this particular packet with this combination already exists or not. If yes, then we will return false as the packet already exists and we will not add it again. But if it does not exist, then we will simply add that packet. Remember, after adding the packet, we need to check the memory limit. If it exceeds, if the number of packet exceeds this memory limit, we need to remove the oldest packet as well here. Next is this forward packet function. So here we will just simply need to return the oldest packet with the combination of the source, destination, timestamp, right? Forward the next packet in FIFO order. The FIFO, that is the whichever packet we have inserted first, right? We need to return or remove that. If we don't have any packet in the router, then we will just simply return the empty string here. The last method is get count. Here we have three input parameter: destination, start time and end time, and we need to return the number of packets with destination as this value and having a timestamp which is in between this start time and end time inclusive. Let's try to understand this with example as well. So we will just simply go through this example one here. So we will first create a router and it will have the memory limit of 3, right? This router will have memory limit equals to 3, which means it can have maximum 3 packet at any moment. Next is this add packet. So let's say our packet or the router packets and router is initially empty. Yes. Now we will have the add packet with this value 1490. So we will first check whether this combination already exists or not. It is not. Our router is empty only. So we will just simply add this packet here and we will return true. Again, we have a add packet function with this particular combination. Again, we see that does this combination exist? No. So we just simply add it here and we return true. Next, again, we have this packet. Okay. So now you see, right? This packet combination already exists. So we will return false here. We will not add this packet. Again, we have a add packet with this particular combination. So it does not exist already. So we will need to add this and we will return true. Again, we have a add packet with this particular combination and since it does not exist, so we add this here. Now see, as soon as we add this packet, our memory limit exceeded. We have 4 packets now, but a router can hold maximum of 3 packets here. So we will remove the oldest packet. Oldest packet means the packet which is added at the very first. So this packet. So now our router we have removed this packet and our router will be like this. Okay, and we return true here. Now we have the forward packet function. So forward packet is to return first packet, remove and return the first packet. So what is the first packet? This one. So we have returned this. Now our router will be like this. Okay, right? We just return this particular value. Again, we have a add packet with this particular combination. It does not already exist in our router, so we just simply add it. Now we have a get count function with destination as 550, start time is 100, and the end time is 110. Okay, so if you see here, we need to return number of packets with destination equals to 5 and the time must be greater than equals to 100, and time less than equals to 110, right? How many such packets we have? Let's go through this packets which we have stored here. So this first packet, it has a timestamp destination as 5, but timestamp as 95. It is less than 100, right? So we cannot return this. Again, here we have a destination of 5 and timestamp is greater than equals to 100, yes, and less than equals to 110 as well. So yeah, we can consider this. The third one did not have a destination as 5, it has a destination of 2, so we will not consider this. So we will just simply return 1 here, only one packet is satisfying this condition. Okay, that's how we need to solve this problem. Now let's go to the constraint so that we will get to know which data structure we should use here. So here the memory limit is maximum of 10 raised to power 5. That means the router can hold maximum 10 raised to power 5 packets. The source and destination is has a maximum value of 2 into 10 raised to power 5 and timestamp has a maximum value of 10 raised to power 9. Okay. Start time and end time will have a maximum value of 10 raised to power 9 and at most 10 raised to power 5 calls can be made to all this function altogether, right? So we maximum these functions we need to call 10 raised to power 5 times. And we have also given that the queries that we will have for add packet will always be in increasing order of timestamp, right? So see, our n, which is the memory limit, is also 10 raised to power 5, and the maximum number of calls that we need to make function is also 10 raised to power 5, which is n, right? So we should have all these functions should have a time complexity maximum of O log m and n log m, where n is the number of packets, which is this memory limit, and m is the maximum number of calls, or sorry, m log n, because m is the maximum calls we will make to any function, right? And n is the number of packets. So the maximum time complexity that we can have, right, should be, we need to choose a data structure such that all these functions can perform operations in maximum time complexity of of m log n, where m is the number of calls made to these functions and n is the number of packets that exist in the router. Okay, so let's understand what will be the data structure we will choose here. So first thing is we will just simply have the router. We will have a router here, so we just simply create one variable which will store the memory limit, and we will just simply assign this memory limit here. Okay, next thing is add packet. So for add packet, we first need to check whether this combination exists or not, and it if it does not exist, then we will simply insert it. But after insertion as well, we first need to check that if it exceeds the memory limit, then we will need to return the first inserted packet from the stored object, right? So if you look into the criteria, we need to perform some kind of FIFO operation here. And for FIFO, which is the best data structure that we can use, it is Q, right? So we will use Q here. Now let's first create one class uh, of packet so that it will be easier for us to handle all this source, destination, timestamp combination. So we will have these three values in this class of packet, and we will call this constructor, which will have input parameter is like this, and we just simply assign this value to this packet. This of destination equals to this destination, and this of timestamp equals to this timestamp. Okay, so here we will have Q, which contains the packets here, right? So it will have the packet, and we name it as like Q. Now we will need to check that whether this combination of packet already exists or not, right? So for that we need to have some kind of hash map which will which through which we will be able to find whether that particular combination exists or not in O of one time, right? So what we can do here is we will have one hash map function. But if we will give this packet now, here the hash map, it will increase our time complexity because handling of the object will be difficult. Like if we will give some kind of integer value, first is a string we can give like a string like source, then we can convert these values into string. But a string is also take some time, right? So the best thing is we will use the into some kind of integer value. So we will have one function which will encode this particular combination of source, time, stamp, and destination into some kind of a hash map, right? So we will call this, and it will just simply return the long integer or the long integer value, where we will just simply multiply source with 10 raised to power 10 plus by 10 raised to power 10, because both source and destination can hold maximum of 10 raised to power 5. So if we multiply it with 10 raised to power 10, it will always give us a unique value. Destination with 10 raised to power 5 and then timestamp. Right, so we'll have this unordered map with long and boolean, which will check whether this particular packet exists or not in our hash map, right? So now again, this function is okay, that we will have the hash map which will able to tell us whether this particular packet exists or not, and based on that we will just simply insert the packet in a queue in O of one time only. So this hold goods. It takes maximum time complexity of O of m. For forward packet also, we will first check. We just simply need to return the first object from this queue. So that also we can, that operation also we can perform in very less time. So it also hold good here. But this particular get count function, right? So here we first need to check what are the packets we have with destination of this value. Now how we will identify that? For that also we need another hash map, and here key will be the destination, right? And what are the values we will need it here? We just need the timestamp, right? So we can use some kind of array like a vector which will hold the timestamp of all the packets with destination as the key value. But does this suffice our problem? We can use vector, but the problem here is that we need to perform that add or insert operation on this hash map as well, right? In these two methods. And if we want to remove that first object, right, from vector, it will take us off and complexity. It will be not easy to maintain that, right? So can we use queue here? If we will use queue, then we will need to find what are the timestamps we have with the start time and end time, with the start time greater than, with timestamp greater than this start time and end time less than this end time. So for that we need to do some kind of binary search, right? Because we want the time complex. This entire method, the operations that it will take should have the maximum time complexity of log of n only, right? And that we can only achieve if we use the binary search here. And remember, we cannot perform the binary search on queue. So what can we use? DQ. With DQ, we will be able to perform this FIFO operations and as well as this binary search. So we will use here DQ, and it will hold the timestamp. Okay. So first is this add packet. So we will first create a packet object P with the source, target, and destination combination. Source, destination, and timestamp combination. We will leave that encoded value as well, right? This P dot get encode. Sorry. Let me just rename this function like this. Get encoded value. Okay. What we will do, we will first check if this contains this encoded value. If yes, then we will simply return false. Here we will not perform any operation, right? That means if packet already exists, we will just simply return false, else we will add the packet. So we just simply add the packet in queue, right? We will add the encoded value in this hash map, and also we will store add the packet in this destination object. So destination of this value, we need to store it like this: push back with timestamp value. Okay, now next thing is we need to check whether after performing this addition, does my queue have packets greater than this memory limit? That if the size of this queue exceed this memory limit, if yes, we need to remove the oldest packet. And how can we do that? So we will just simply do, we will just first get that old packet, right? Old packet will be from this queue, which we can directly get as like queue dot front. And then we will remove this packet. So we just do simply queue dot pop. Now we need to find the encoded value of this old packet so that we will update the same in our hash map. So we will have long. I will just simply add this as like L old encoded is equals to this old p dot get encoded, and I will just simply have this value as false here. Okay, but does here the having this hash map is a good idea? Because although we are removing this, but we are setting this value as false. So this will actually is increasing our memory and space complexity as well. So instead of using this unordered map, we can use unordered set. Unordered set has also the average time complexity to find whether that any particular key exists or not will always takes O of 1, and that removing of that key will also take off one time complexity only in the average cases, right? So we can use the unordered set here. So for that, instead of doing like this, we can do like this as dot count of this encoded value. If it is greater than 0, that means this encoded value already exists in our set. So we will return false here. And if not, then we will just do simply insert. And similarly here, we will get the old encoded value, and if it is not exist, then we will just simply remove this from the set. This old encoded. Okay, now we have removed it from queue, we have removed it from set, now we will remove it from destination as well. This destination map as well. It should be another map, sorry. So what we will do, we will first, so remember here, this destination of this all p dot destination which returns me the DQ of all the packets with this particular destination. And can we just simply remove the first element of this particular DQ? Yes, because we are removing the oldest packet, so it should be inserted at the very first position only here as well in this destination unordered map, right? So we can just simply do pop front. Similarly, now let's implement this forward packet. So similarly, we need to perform this particular operation only. We will first get the old packet or the very first packet which is inserted, right? And then we just simply need to remove from here. Q dot pop s dot erase and then this. And then we will just simply return the source destination and timestamp of this. But before performing all this operation, we should have one more check, that if queue dot empty, that means we don't have any packet in our queue, then we will just simply return the empty array here. Now let's implement this get count function. So for getting all the packets, we will first get, so here we will use the lower bound and upper bound function. So first we will get the get index which has timestamp greater than equals to this start time. Get index of first element. And how can we do that? With the lower bound function. So we will have int I is equals to lower bound of this destination, right, comma, destination of this dot and comma start time minus this begin. So it will return give us the index of the first element which has timestamp greater than equals to this start time. Now we want index of first element which has, because all the elements here are stored in the ordered way of timestamp, because that's how we are adding this, we are always gather the packets in increasing order of timestamp, so we can just simply do this operation, we don't need to sort anything here, right? So now we will get the index of the first element with timestamp greater than this end time. So whatever the elements that we have in between these two will give us the number of packets which has the timestamp which are of the destination with this value and the timestamp in between this start time and end time. So we will just simply use the upper bound here instead of lower bound. And here we will give end time. Okay, and now we will just simply need to return j minus I. So j minus I will give us the number of elements which exist in between these two indexes. Okay, now let's try to run the test cases here. Is there any? Okay, I forgot to do this dot source. Let me do like this. Okay, I forgot to write the semicolon here. Oh, okay. We haven't initialized this as public. First, I need to make this as public. It is get input, not encoded. I have made so many mistakes here. It is also in code. Yeah, here we need to return the true if we are able to perform all the operation. And this will be like encode. Okay, our test cases are accepted. Now let's try to submit this. Okay, so our solution is also passed. Now let's try to understand the time complexity here for each function. So first this add packet. So this add packet here, uh, we are first doing, we are creating an object, then we are just simply pushing this. First we are checking whether that particular encoded value exists or not. So as I mentioned you already, the set, this unordered set, in the average case, it has a time complexity of this count function as O of 1 only. So this is being O of 1 in average cases, right? So push is also O of 1, right? Insert will also be O of 1 in case of unordered set, and this destination and then pushback is also will take O of 1 only. Pushback function will also here taking O of 1 only. And this will write that getting the front element of 1, removing the front element also O of 1, erase will also take O of 1 in unordered set, and it will also take O of 1. So maximum time complexity, at every time it is taking O of 1 only, and for m iterations it will be like O of m. So similarly this forward will also will take O of m time complexity. And now this get function, so this lower bound will take O of log n, where n is the number of packet it can have, right? And similarly this upper bound will also can take O of log n. So maximum time complexity that it can take is O of m log n, right? So here thus we have solved this problem in maximum of O of m log n time complexity. I hope you understand this problem. I hope you understand how we are using all this data structure which through which we can perform all these operations in the given time complexities, right? Please do solve the solution by yourself after watching this video. Please do not copy paste the code here. Once you solve this problem by yourself, you will gain the confidence and also you will understand this problem more. If you like this video, please do share and subscribe. Yeah, thank you. See you in the next video.